Investors poured over $100 billion into AI software, but the bottleneck for scaling models has moved out of code and into the physical world. Data center electricity demand is projected to roughly double by 2030. Operators are hitting hard limits on facility cooling capacity and hardware supply chains. AGI-class systems function as persistent, multi-domain architectures that continuously consume distributed compute, coordinate massive data pipelines, and interact directly with physical infrastructure. The critical failure point is how we manage that hardware. Right now, the routing network, the compute fabric, the power grid, and the security plane are controlled as isolated silos. Legacy routing tools, workload schedulers, and zero-trust systems attempt to evaluate the network by collapsing complex, high-dimensional operational telemetry into simple, one-dimensional scalar weights. To run autonomous AI safely, the infrastructure requires a unified, predictive control layer capable of processing high-dimensional data in real time. This diagram shows a candidate architecture for that layer, developed by Tensor Networks. It combines a Predictive Tensor Control Plane, or PTCP, with a reconstruction and audit layer called TNQG. Without this mathematical control, AGI infrastructure remains vulnerable to catastrophic, unbounded failure modes, where an autonomous agent could easily violate physical data center limits. To understand how PTCP works, look at the telemetry fire hose. A modern network is constantly flooded with port counters, queue depths, identity postures, power readings, and security events. If you try to map all of these variables together to see how they interact, you encounter the state-space explosion problem. You end up with an exponentially massive probability tensor representing the entire system. Storing that full tensor requires an exponential storage footprint. It's computationally impossible for a controller to process. PTCP resolves this using tensor train compression. This reduces the memory requirement from exponential to linear, fitting cleanly inside active memory. Crucially, this compression preserves the cross-modal structure of the network. The controller still sees exactly how a spike in thermal power correlates with a shift in security identity without needing a massive state table. This process allows PTCP to maintain a continuous, predictive pattern of life model directly inside the local controller. By solving the compression problem, the system can forecast an extreme congestion event or a power transient forming in the physical fabric long before legacy retrospective dashboards can display an alert. Once the controller has this compressed pattern of life model, it has to use it to route workloads and place jobs. PTCP accomplishes this by mapping the predicted state of the network into an operational geometry. Efficient paths with high bandwidth and low energy cost are rendered short, creating smooth topography. Congested or overheating paths are rendered long, forming sharp peaks. The algorithm routes around these by minimizing expected cost and adding a strict penalty called conditional value at risk, or CVAR. That CVAR term explicitly penalizes the upper tail of the risk distribution. It forces the controller to mitigate the absolute worst-case scenarios, rather than just lowering the statistical average. Average latency is largely irrelevant in an AI factory if a single P999 delay causes a multi-million-dollar training cluster to completely stall. By routing through predictive geometry, PTCP prioritizes avoiding catastrophic infrastructure failure over chasing marginal improvements in mean speed. This introduces an obvious security risk. A hallucinating model could propose an action that crashes the physical network. PTCP prevents this through its core safety rule. It completely separates mathematical optimization from physical actuation. Before any command is executed, the proposed action is projected into a bounded safe set. This strict physical envelope ensures the action preserves reachability limits, capacity rules, and rollback constraints. A bad prediction might temporarily degrade routing efficiency, but it cannot bypass the hardware's encoded safety invariants. That projection controls the actuation. The second half of the architecture is Tensor-Network Quantum Gravity, or TNQG. Looking back at the diagram, TNQG sits beneath the control plane. In this commercial context, it is deployed as an operational reconstruction program, not a proof of theoretical physics. TNQG serves as a diagnostic dictionary, mapping tensor states against physical observables like distance, curvature, and capacity cuts. Through residual testing, the system compares predicted geometry against physical reality, immediately flagging model drift or topology defects. PTCP decides the bounded action, and TNQG audits the geometry. Together, they form a mathematically honest control loop that safely governs autonomous infrastructure. The combination of state compression, predicted geometry, safe actuation, and residual auditing forms a strict capability superset. It includes baseline reactive control as a fallback, while creating measurable upside. The initial commercial application for this software wedge targets physical hardware, specifically optical circuit switches like Lumentum's R300 and R64 platforms. Optical hardware is a valuable, high-capacity physical asset, requiring an intelligent software control moat to maximize its lifespan. This diagram outlines the PTCP value stack. Because the mathematics of the control plane are portable, the exact same logic maps horizontally to entirely different industries. Across hyperscale AI factories, cybersecurity operations, energy grid orchestration, and industrial robotics, the core control problem is mathematically identical. The input sensors and output actuators change based on the industry, but the central algorithmic kernel remains static. Tensor Networks is building a horizontal control substrate, applicable wherever complex systems converge. For investors, evaluating a control paradigm requires a disciplined, falsifiable standard of proof. The required evidence comes down to strict empirical metrics: compression fidelity, absolute reductions in P99 latency, zero reachability violations, and quantifiable energy improvements. This framework structures a milestone-based investment path, gating capital and de-risking the technology at every stage. During the alpha JDA phase, the PTCP controller prototype must pass strict kill gates in a physical lab twin environment before advancing to strategic equity pilots. This process ensures that the software proves its mathematical claims on actual physical customer hardware before attempting broad market expansion. Scaling AGI demands a management layer capable of governing the physical state of the infrastructure itself, reaching beyond the limits of model training and hardware acquisition. True enablement and control requires an infrastructure layer equipped with the mathematics to measurably say no, roll back unsafe actions, and audit its operations.